Yeah, hi everyone. Thanks very much, Michal, for the nice introduction. Also for the invitation, and also for putting together this workshop. I was here for the last workshop 2 years ago, and I enjoyed that very much. So I'm looking forward to this week. And so yeah, so my talk is about double microwave shielding. So this is a bit of an overview. I tried to put a few new things in there, and given that there's some overlap with Jeremy's talk, I may actually get to them. Okay, so first off, for motivation, so we're talking this week about ultracold molecules, which we want to use for various sort of big picture applications. We're interested in cold molecules as a platform for chemistry in a quantum mechanical regime. Also to use these molecules for quantum computing, for quantum many-body physics, quantum simulation, and precision measurement. So these are kind of the big picture applications that I'm sure we'll hear about this week. And I'm not going to very explicitly talk about any of these, but I guess the whole shielding business is related to this in that it enables cooling, which will benefit all of these applications. So how's this related to cooling? This is through evaporative cooling. This is the technique how you get to the lowest temperatures. And this is done for typically also for atoms. And the idea is very simple. You have your atoms or molecules, in this case, contained in some controllable trap, an optical trap, and you can lower the depth of that trap to evaporate the hottest particles and obtain a colder gas. So the point is that this whole process is efficient if loss is slow compared to thermalization. And so this can typically be done for atoms, but molecules have the problem that they have this fast collisional loss. So again, to explain where this collisional loss comes from, I have the same examples as Jeremy. So I'll skip through this, but the idea is that loss in a molecule like KRB can be modeled quantitatively by a simple model that's called universal loss. And this basically says you model the long-range interactions, let's say von der Waals attraction, and whenever molecules come close together, you assume that they are lost with 100% probability. And that simple model quantitatively explains experimental observations. And it motivated subsequent experiments where the molecules are non-reactive, so you know that any binary collision cannot produce some different product, and that should eliminate these collisional losses if they have been due to chemical reactions. But surprisingly, you see much the same loss. These non-reactive molecules have fast two-body loss that is near the universal rate. And this is not fully explained, as Jeremy mentioned. There are some key ideas. So John Bone proposed this idea of sticky collisions, where the idea is that ultracold molecules, when compared to atoms, in collisions, they stick for a very long time due to the high density of states of these complexes, and that enables some sort of loss process to occur during this sticking time. So we put forward the idea that that loss process may be excitation of the collision complex by the trapping laser, and this was partially confirmed by experiments on KRB and also rubidium cesium molecules. This is in Simon Cornish's group, where you modulate the optical trap and you see that the loss is reduced. So it seems that photoexcitation explains loss of rubidium cesium molecules, but somehow this doesn't actually describe what happens in other molecules such as sodium potassium and sodium rubidium, where if you repeat this experiment, you don't see a suppression of collisional loss. So this is not a fully resolved question, what actually causes the loss. But again, as Jeremy mentioned, we can deal with this by controlling long-range interactions. And the idea is to swap out this attractive von der Waals interaction for some sort of repulsive potential that prevents molecules from coming close together and prevents this collisional loss, no matter what causes it. And there have been many ideas of how you can do this. So I think the most intuitive one is in 2D, If you confine your molecules to 2D and polarize them perpendicular to it, then the interactions for any sort of in-plane collision are repulsive, and that should shield the molecules. And so that's been implemented also in experimentally in the group of Junyi at Jilla. Also, there's this idea of static field shielding, which Jeremy explained, was proposed by John Bone and also implemented in Junyi's group. And there are many other proposals that maybe we'll see during this week. So there's proposals to use Raman transitions. There's even a scheme specific for polyatomic molecules. And I would like to talk about microwave shielding. So this is a bit of a cartoon to explain where the repulsive interactions come from in microwave shielding. Jeremy also explained this. So this is showing the interaction potential for ground state molecules, which is attractive. And the idea is to address these molecules with a rotating electric field that rotates at the frequency of the rotational transition. And so that gives you a additional threshold if you look at the energy levels in a sort of field dressed picture where you've excited one molecule, but you've absorbed one photon. And so for blue detuning, that's below your initial state. And it gives rise to an attractive, but also a repulsive potential. And so that repulsive potential crosses your ground state. And if you increase the Rabi frequency, that crossing becomes avoided. And so hopefully the molecules follow that upper potential adiabatically, and they can scatter elastically for thermalization, but not inelastically. Of course, they might undergo a non-adiabatic transition and then still reach either short range or that this additional threshold down here, which are loss processes. So together with Jeremy, we studied this, not at this cartoon level, but quantitatively by numerically exact coupled channels calculations. And so this is the main result showing loss rates due to these two mechanisms as a function of the microwave parameters, so detuning and Rabi frequency. And so the message is that you can find microwave parameters where you can really suppress collisional loss by many orders of magnitude. This can be done using circularly polarized microwaves, and if you use linear polarization, you see no suppression of collisional loss. So before anyone actually tried to implement this, of course, people started asking, well, if it works for circular polarization but not for linear, then exactly how close to circular do I need to be? So we also studied that quantitatively by studying shielding in an elliptically polarized microwave field characterized by this ellipticity angle psi. So zero angle is circular polarization. And you see if you have some ellipticity, then the loss rates really go up quite quickly. So you can shield, but it's best to do this with only a few degrees of ellipticity, which is challenging but can be realized experimentally. And the second question is, so far I've not talked about hyperfine, and Jeremy has not mentioned this either. But before we studied this, it wasn't clear that this wouldn't ruin the shielding. And so we also studied this again by coupled channels calculations, and indeed you can see that the hyperfine interactions can lead to all sorts of additional losses and really increase loss rates by orders of magnitude here. Fortunately, we also find that you can really suppress this by applying a very modest magnetic field. So in practice, this isn't really an issue. And so I think these sort of quantitative studies really were helpful in guiding experimental realization. So this has been realized first in John Doyle's group at Harvard in collaboration, and then also, so that's on calcium fluoride molecules in merged tweezers. Also in bulk gas of fermionic sodium potassium molecules at MPQ. Dajun Wang has also realized this in their sodium rubidium molecules. I guess we will hear about this tomorrow. I was not involved in any of that. And then in the rest of this talk, I'd like to talk about this collaboration with Sebastian Will's group at Columbia, where we're shielding sodium cesium molecules. And this has recently led to the first BEC of polar molecules, which again, we'll have a BEC session tomorrow morning. So we'll hear a lot more about this. Okay, but first off, we started just trying to apply this, what we might now call single field microwave shielding to sodium cesium molecules. And the main result of that study is shown here. So this shows the two-body loss rates as a function of the detuning. And you can see that the experimental loss rates, the markers, are very well described by the coupled channels calculation, the shaded area. And you can really achieve about the 2 orders of magnitude decrease in collisional loss. But then if you want to decrease loss further, this two-body theory tells you to reduce the detuning further. And when you do that, you see some sort of additional loss that isn't described by that two-body calculation. And so we think, and I will show something in a few slides, but we thought that this might be due to 3-body recombination. And the sort of additional hint is the temperature dependence here, which is very different for this additional loss compared to the 2-body loss. So what's happening is that we're dressing molecules with this circularly polarized microwave field, which creates a repulsive potential at more than 1,000 Bohr radii separation. So this is really a huge shield around the molecule. But outside that shield, there are dipolar interactions, as Jeremy mentioned, and that causes this little potential well, which is very shallow, but it can actually support a bound state. And once you have that, you can have 3-body collisions that cause recombination into that bound state. So the idea for dealing with this is just add another microwave field, which is linearly polarized, and we use this to compensate, to cancel that dipolar interaction outside the shield. So how does that work? Well, so this is a bit of animation of where these dipolar interactions even come from. If I apply a linearly polarized microwave field, I induce a dipole moment in the molecule that oscillates along with the field. So on time average, that dipole moment is 0. But if I do this for 2 molecules, they oscillate following the same field, so the dipoles are always in phase. And so if they're on top of each other like this, the interaction is always attractive and it doesn't average to 0. And if you work it out, it's just a dipolar interaction, except the effective dipole moment is controlled by the field Rabi frequency and the tuning. For circular polarization, it's similar. You have a rotating dipole moment, and 2 of them are always pointing in the same direction. In this case, they're head to tail for the same orientation as before. So now we get again a dipolar interaction with the dipole moment controlled by a different field. So this is independent, and the sign of that interaction is flipped. So if I somehow have both at the same time, I should be able to cancel this dipolar interaction. Okay, so this is shown here. So the idea is that compared to the single field case in orange, we can really reduce this attractive potential if we can compensate the dipolar interaction, causing that completely repulsive potential. Or we can take that and then slightly detune one of the microwave fields so that you induce some dipole moment, but still really reduced well depth here. So the idea is that by doing that, you can expel all bound states from the potential. So this is showing the number of bound states as a function of the detunings for a fixed Rabi frequency. And you can see here there's a huge parameter space where you have no bound states, but you can still tune interactions. Okay, so then the question is, does it actually work? We've said you need perfectly circular polarization, and now you're adding a linearly polarized field. So does the 2-body shielding still work? Actually, we find that for this double shielding with 2 fields, the shielding is better than in the single field case, in particular around this compensation point, which is where we want to operate. So this looks good. What about 3-body loss, which was, again, really what we were trying to prevent? So this shows experimental 3-body loss rates as a function of the Rabi frequencies. And here at the center, between the vertical dashed lines, you see a region where there's no bound states in the potential. And 3-body recombination is small. It's really essentially 0. It's at the detection limit. Once you go outside that region, then pretty much where we expect the bound state to sit, we see that the three-body recombination rate goes up by orders of magnitude, and you have this fast three-body loss. While we're at this, we can also quantitatively compare the two-body loss rates to experiment, and you can see that actually the measurements are in good agreement with my coupled channels calculation, this line, in this limited region where the two-body loss is so fast that you can actually measure it. For much of parameter space, it's essentially below the detection limit. Okay, so then with two and three body loss essentially removed, you can efficiently evaporate sodium potassium molecules. And I will not talk much about this. Sebastian will talk about this tomorrow. But you can evaporate to a quantum gas, so to a Bose-Einstein condensate of polar molecules. So you now have a quantum gas of molecules under this double microwave shielding. So you have a quantum gas where you can now control interaction. So this is very powerful as a platform for quantum many-body physics. So interactions in the system can be maybe quantified by two length scales. There's a length scale associated with the dipolar interaction, and there's also a scattering length, although we might hear about some more philosophical talk about this later. In any case, here at around 6 megahertz, there's the compensation point where the dipolar length goes to 0, and the interaction potential is completely repulsive. And so a repulsive potential guarantees to have a positive scattering length. And so this is very nice for making a dilute weakly dipolar BEC that's stable against collapse, that you're guaranteed, no matter what molecule you have, you're guaranteed to have a positive scattering length. Then you can detune from this compensation point and you get control over dipolar interactions, and it becomes stronger. You can choose the sign of this interaction, and at some point you hit this resonance where a two-body bound state appears. You get a scattering resonance, and the scattering length should go from large negative to large positive values. So in between these two resonances, you have no bound states, and the scattering length is guaranteed to go from positive through 0 to large negative values. So you can basically choose the sign of either of these and tune their relative magnitude. So you have comprehensive control over interactions in the system. So then briefly about universality, which Jeremy already talked about, and there's also a poster by Joy Dutta about universality in microwave shielding. Just some comments on how this works out in double shielding. So the main issue is that now you have more microwave parameters. You have 2 detunings and 2 Rabi frequencies, and these are all dimensionful quantities. But clearly there's some universality. If I look at shielding for different molecules, they don't look the same in these plots, but there's some similarities, right? So basically what I want to do is simplify this by eliminating some of these parameters. So the first thing I can do is I can fix one of the parameters, let's say the pi detuning, to require compensated dipolar interactions. That eliminates one parameter, and I can look at the loss rates, in this case as a function of sigma detuning for different Rabi frequencies. This is a really limited data set, but you can see that the shielding appears to be best when the sigma microwave is on resonance. And again, the pi one is off resonance to compensate interactions. So we can fix sigma on resonance, and then we only have 2 parameters left, the Rabi frequencies. When I fix also the ratio of these, then I have only one dimensionful parameter, which just scales the energy levels of these, the field stressed energy levels. And then the conclusion is pretty simple, just the larger the Rabi frequency, the better the shielding. And so it's important that you take this ratio, which is non-dimensional. If you don't do that, you fix one of the Rabi frequencies and scan the other, you get a lot of structure that doesn't appear to be that regular. But if you take that same data and look at this as a function of the ratio of Rabi frequencies, then you see that all of the structure is universal. It has nothing to do with the nature of the molecule. It's just the field stressed energy levels in the presence of these 2 fields. So yeah, you can look at different molecules, and what you find is there's a lot of structure that again is completely universal. These peaks are all in the same positions for all molecules. And in the troughs where the shielding is best, you see a clear hierarchy where just the more heavy and the more dipolar your molecule is, the better the shielding works. And so, you know, if you're working on silver, this looks pretty good. Okay, so then I'd like to say something slightly, well, I'd like to say something about what about the residual loss and what determines this, but this will get slightly more technical than what I was just saying. So basically what we're doing is we're dressing ground state molecules on these first rotational transitions. And that induces some oscillating time-dependent dipole moment. And that time dependence can also be described in a sort of Floquet picture by talking about photon numbers. So basically the relevant energy levels is just the ground state with some reference number of photons in two fields at different polarization, different frequency. There's the sigma excited state, so Jm equals 1, 1, and you've absorbed one sigma photon. And there's this pi excitation where you excite to 1, 0 and you absorb a pi photon. All other energy levels are basically the rotational constant away, so they're gigahertz away, whereas these are spaced by 10 megahertz or so. Then what you can do is you can increase the Rabi frequency. These levels are coupled, so they just split. And this is about it. Well, actually, there's a peculiarity with these two fields is that you can, for every level that you get, you can make a whole ladder, exchange, basically emit a sigma photon, absorb a pi photon, and this is just spaced by the, you know, the difference in detuning. At a single molecule level, that's completely irrelevant. You cannot just simply swap out sigma for pi photons because there's an angular momentum constraint here. But now if I look at the collision between two molecules, the dipolar interaction between them can actually transfer angular momentum from the molecule to the relative orientation, and then all this stuff can happen. So you get down here at 10 megahertz detuned, you have the sort of normal field stress levels. And then in between, we get a lot of additional Floquet levels. And it turns out that most of the inelastic loss just tends to go to the nearest level. So it means that the energy release in these collisions is much smaller than it typically would be for single field dressing. So if we look at the loss rate, and I just exclude these additional Floquet levels, which I shouldn't do, but if I do that, then the loss rate drops by additional orders of magnitude. So this really determines the loss. You can also see that when you look at the energy release in an inelastic event, in the single field case, this is just the Rabi frequency, and it increases a bit when you increase detuning. But in the double shielded case, you see all this structure. So you basically, when you tune the detuning, all of these field stress levels, they move around, and a level can cross the initial state. The energy release goes to 0, and you actually get the corresponding peak in the loss rate here. So this is where all this structure comes from. This is not just a peculiarity, this may actually be something that you can observe. So you might say, okay, wherever you go here, you're releasing either a few or 10 megahertz energy, and this is just a loss process because these molecules are not trapped. But actually, these molecules, they when they're dressed, they have such long-range interactions that elastic collisions are very fast. Just as a reminder, in sodium potassium at MPQ, thermalization is in a hydrodynamic regime. It's not limited by by elastic collisions, but rather by motion in the trap. So the mean free path is actually short compared to the size of the gas. And so if you have a collision that releases energy, that molecule is not immediately lost as it would be in a typical ultracold atoms experiment, but it can actually hit additional molecules on the way and impart part of that energy into the rest of the gas. And so this is a kind of idea that we're looking into, whether this is, and so we're trying to model that quantitatively with Ruben Wang at ITEMP. But here's a sort of preliminary experimental result where we actually see additional three-body heating that we think might be due to these sort of chain reactions of elastic collisions of the lost molecules. I also had something that I thought would relate to Jeremy's talk, but he didn't actually talk about this, which, okay, the red light is flashing, so I will skip this, but you can ask. Yeah, so sorry about this. So yeah, just to conclude, so I've discussed double microwave shielding. This name has a kind of double meaning because we're not only using double the microwave fields, a sigma and a pi polarized field, to shield from double the loss mechanisms, two-body and three-body loss, but also you get control over the remaining interactions, both the scattering length and the dipolar interactions. And so together, so this enables evaporation to quantum gases of these molecules where you get comprehensive control over the interactions in this quantum gas. And so that really makes dipolar molecules now a sort of mature platform for quantum many-body physics. So I think this is a very exciting prospect. And in view of all of these developments, there's a lot of interest, and just like to flash that in fall next year, there will be a KITP program on ultracold molecules organized together with Anastasia Borshevsky, Hossein Sadakpour, and Michał Tomza. And so this is super far away, fall next year, but actually the deadline for applying is already this fall, so I thought I'd advertise it. I hope to see many of you there. Thank you very much for your attention.
Thank you. I think for Santa Barbara, most of the theoreticians here will get invitations soon.
Yeah.
Thank you. Lovely talk, Tijs. So I have comments and a question. For the breakdown of universality, the non-universality, I didn't talk about in detail about what we saw because it's on Joy Dutta's poster, but what we did see is that although the breakdown of universality is fairly small in our case and only happens at quite high fields, Rabi frequencies, it does depend very strongly on the basis set we use, and in particular it changes a lot when we include n equals 2 basis functions. And that's basically because even the monomers, once you get to the high enough Rabi frequencies, even the monomer states are getting significant mixtures of n equals 2. Do you know anything about how your non-universality depends on basis set size?
I'm not sure. I'm also not sure what I said about non-universality.
Well, you showed pictures for different molecules and they weren't the same.
Well, yeah. So I think the point there is the point you were making is you have to choose the axes, right? So what we did there is you fix some Rabi frequencies and then scan a detuning and see what it looks like. But that's not, in the reduced units, that's not the same for different molecules.
Okay, so different reduced energies for different molecules.
Oh, okay.
Basically.
Or are you talking? I'm sorry. Are you maybe talking about this?
Yeah, that's the sort of thing.
No, I think this is.
But perhaps that's for the same energy for all molecules, in which case, because in order to get universality, we have to do the same reduced collision energy for all molecules.
Yeah. Well, I think, okay, so I think this is not in reduced units, right? So this is, I mean, it's not the same, but the point is the structure, like the position of the peaks, that's due to the field rest levels, and it has nothing to do with the structure of the molecule. So in that sense, so yeah, okay, so this is not really a dimensionless universal plot, and how strong certain peaks appear is different for different molecules in this case, but that's again because the axes are dimensionful. The point is the structure that you see has nothing to do with the molecule. So in this sense, I'd say this is showing universality.
Thank you.
So in the meantime, I'd like to ask about skipped slide.
Yeah, so I thought Jeremy would mention he has this paper with Bijit, who's also speaking this session, and then Caden is absent. But I think this paper really came about at the last workshop here. There's this idea that if you do shielding, you can put molecules in different hyperfine states, and the shielding will work irrespective of this, and the interactions are the same in every hyperfine state. And so this realizes SUN symmetry. So this is interesting because you get some behavior that is due to quantum statistics and not the dependence of interactions on the state. So the idea was, okay, but you can still ask, if I want to make my interaction state dependent, can I do it with shielding? And so the idea that I wanted to put forward is to encode pseudospin not in nuclear spin states, but in vibration. So the idea is that you change molecular constants by a very small amount, relatively speaking, but actually in absolute units, the change in rotational constant, this is for sodium cesium, a number, is 6 megahertz. So this is kind of on the same scale as detunings and Rabi frequency. So you basically, for different vibrational states, you have a different effective detuning, and that detuning controls the dipole moment. So you can actually control dipolar interactions. They can be different in different vibrational states, but you can tune how different they are. So it's completely controllable. That's, yeah.
Arthur?
Yes, I have a question about the simultaneous tuning of the scattering length and the dipolar length, which you very nicely showed for the NACS, like the nice curve. So I was wondering if you get a similar figure also for fermionic molecules, or if it looks completely different.
To look at what would be the scattering length?
I mean, for dipolar fermionic molecules,
Yes.
you should also get the equivalent of a scattering length.
Yes. I mean, it would. Well, yeah, and this would also diverge at these resonances. So that's, yeah, I'm not sure what it's. I guess so. I guess you could do something similar to this. Yeah. Yeah, not sure what to comment about this. Yeah, you're right. This would probably be sort of exactly the same. Okay. You get, I think, different scattering lengths for different directions. But yeah. Okay, cool.
Oh, yes.
Thanks for the very nice talk. Actually, since you're on this slide now, the competing systems of magnetic atoms, where would they be on this slide roughly? I thought about dysprosium, for example.
In absolute units, I mean, these lengths, they are huge, right? So
Right.
for magnetic atoms, this is more on the 100 scale, I think. Of course, if you're talking about the completely universal physics where you care only about sort of the ratio of scattering length and dipolar length, then you can do some things. But I mean, in absolute units, this is very different. And I think one of the key differences will also be that you can sort of turn off loss here, which should mean that you can go to higher density, which if you're computing, let's say, the mean dipolar interaction energy, that could buy you a lot. And that could put you even in strongly interacting regimes where magnetic atoms, well, it's at least hard to get to. Yeah.
Please, the last question.
Oh, that's good. I hope it's important enough. So I very much liked your picture of the dressed states and how you can swap from pi to sigma and vice versa in a collision. But this is not all bad, right? You can also be lucky, or you can tune your Rabi frequency sort of in a clever way so that you get also cancellation, right? There are also these minima in between peaks, right? So it's not all necessarily bad, but you can be lucky.
Yeah, and actually in this plot you can see there's some regime here where you kind of don't see all of these peaks. So you can actually complete this avoid this altogether.